Well, welcome, ladies and gentlemen, to this first plenary session on emerging Earth observation capabilities for developing metrics and indicators to monitor environmental policy. So my name is Keith Takeley. I'm the interim Earth observation policy lead for DEFRA. And in a moment, I'm going to introduce my colleague, Beth Cole, senior advisor in Earth observation at Natural England. But I just wanted to set the context and by way of a bit of an introduction to this plenary session. The role of Earth observation in providing metrics and indicators to reliably inform, validate and monitor policy is becoming increasingly possible. Improved precision through satellite improvements in satellite instrumentation, through those on other platforms such as high altitude pseudo satellites and drones, through enhanced temporal and spatial resolution and sensitivity, make Earth observation data more trustable for use in policy monitoring. Ongoing work towards enhancing calibration and validation further supports its use in this area. As the UK focuses on both its international commitments emanating from COP26, as well as domestically on net zero, national adaptation planning, the 25-year environmental plan, amongst others, the increasing trustability of Earth observation data is opening up a new set of metrics to inform and monitor these initiatives. This session will focus on metrics to inform, this session will focus on this evolving Earth observation landscape and how it can be used to support policy development, identifying new metrics to more accurately monitor environmental policy and how effective existing policy is. So I just want to thank, before I hand over to Beth, the organisers, NCEO, the Remote Sensing and Photogrammetry Society, Satellite Applications Catapult, and the sponsors for this session, Taylor and Francis. The presentations will be the normal 12 minutes length, and then there'll be some time for questions after each presentation. Without further ado, I'm just going to hand over to Beth Cole to introduce the first presentation.
Hi everyone. So first of all, kicking us off, we have Miles, he's from Natural England as well, so a colleague of mine, and he's going to talk to us on behalf of the whole Living England team. So this is a project that's lots of people been involved with, and it's part of the Natural Capital and Ecosystem Assessment Programme, directly looking at habitat mapping, a probability habitat map for the whole of England, and it feeds directly into some of these policies that we've been talking about. So over to you, Miles, and off you go.
Good morning. Thank you very much for coming along to learn a bit more about the Living England project. There we go. So, Living England aims to combine satellite imagery, in-field habitat records and machine learning to produce a national habitat probability map. The project's been going for about 5 years now, and we hit a major milestone this year with releasing the product under an open government license for the first time. The project is funded through a couple of DEFRA programs, ELM and the Natural Capital and Ecosystem Assessment. And just a little bit on the NCEA. This is a multi-organisational programme aimed at looking into how we gather evidence on the extent, condition and change over time of environmental assets throughout England. This evidence takes multiple different forms. That can be in-field surveys, citizen science work, modelled outputs, as well as more kind of guidance work on how to gain permissions to do this work, how to collate this data, and how to store it. So back onto Living England, we've got a workflow here of how we create our habitat probability map. As you can see, there are quite a few different steps there that all interact with each other. We've grouped these into 7 broad analytical themes, and I will touch on each of these throughout this talk to give just a taste of how we go about producing our product. So with any model, you need data. So we have 2 main types. The first is field data, used to help train the actual machine learning modeling and validate it. For Live in England, we use both historical surveys from Natural England that have been repurposed for our project. And we also use the Natural England field surveyors who go out there and collect data specifically for Live in England. To assist with this, we have used a couple of Esri products to help with the data collection. So we have a bespoke mobile app that allows the field surveyors to see the previous classification and satellite imagery that has informed that to help create field data points that are representative of a habitat. We've also got a dashboard and web apps that help plan surveys and identify where we need more training data to inform the model. In terms of the actual model, we need geospatial layers. So for satellite imagery, we use Sentinel-2 and Sentinel-1 mosaics. We have a spring and an autumn mosaic created in Google Earth Engine. We also have our in-house processing flow to create Sentinel-1 coherence data layers. So if anyone saw Chris Moore's talk yesterday, he talked through kind of how we go about doing that. We also bring in a range of other ancillary data sets such as terrain, geology, climate to help refine the geographical situation of the habitats within the random forest model. The next step is to prepare the data ready for our model. So on the left there, you can see how we split up England into distinct regions that we term biogeographic zones. These are derived from national character areas and Sentinel-2 orbits, and each one is modelled individually before being combined into a final national habitat map. The reason we do this is the challenges of getting cloud-free Sentinel-2 imagery. So it's challenging enough with these rather large regions. It would be almost impossible on a national scale. So the actual image dates that we use for each region can vary ever so slightly depending on when there is cloud-free Sentinel-2 imagery. On the right-hand side, you can see an example of our in-house cloud masking tool that we use to create the mosaics. And then in the middle, there is an example of the data QA process we use on the habitat records. We do this because, as I mentioned, we do bring in historical surveys, and this helps identify if any of those habitat points have changed land cover since they were collected. The next step is segmentation. So Live in England is an object-based classification. And we use the Sentinel-2 satellite mosaics as well as e-cognition software to create a segmentation, as you can see there. There's a lot of segments. So the released product had just under 7 million segments. So it takes quite a while to process through all of that. On to actually classifying these segments, we have 2 approaches. The first is what we've termed the vector-based classification. And for this, we've developed a number of rules between specific habitat layers that we know are high accuracy and the segments to automatically classify these. An example of this is the Environment Agency Coastal Saltmarsh dataset. That dataset is collected via aerial surveys targeted at low tide. Obviously, with our image mosaics and the Sentinel-2 orbits, it'll be very hard to actually capture those specific timings. So we basically classify any segment that has kind of 50% overlap. So you can see in the top left of the map there, the turquoise, and then after it's gone through the vector-based classification, this is what it looks like. We also do this for water, urban, arable, and bare ground. The remaining habitats are classified via a random forest machine learning algorithm. So the infield habitat records and the segments that they fall within are split into separate training and validation subsets. The training subset is then used to create over 500 separate decision trees. The spatial statistics from each of the remaining segments are then run through these decision trees, with the most common resulting habitat put forward as the A prediction in the probability map, with a probability score from the percentage of trees that have returned it. Live in England also comes with a B prediction for habitat, which can be quite useful for identifying where segments are a bit more mixed or in transition. In terms of a classification framework, Live in England uses a modified version of the UK BAP detailed classification. I say modified because we've made some changes specific to the project based on what we feel we're able to reliably map based on the input data sets and the resolution. An example of this is a combination of acid, calcareous and neutral grassland into a single class. Once we've done the modelling, we undertake a couple of validation steps. One is a desktop-based approach, where we interrogate the output classification against aerial imagery and satellite data sets. At the moment, this is primarily done to help inform field survey work, identifying where we need more training data. However, we're actively looking at including this into the actual modelling workflow to help update the map product before it's released out to the public. The bottom example that you can see on there is another piece of work that's in development, which is a reliability score. So each segment will come with a confidence descriptor based on the habitat probability for that segment, as well as the number of field data points that have fed into the classification. So I've talked about how we create Live in England, and here is the final product. So this is the phase 4 habitat probability map. The statistical assessment came out with a probability of 88%, although we are aware that there are certain habitats or regions where we have a little bit less confidence in that value. So there's the national map. I thought I'd do a quick tour around some parts of the country so you can see a bit more of the detail. So we've got the Lake District here, and this is a good example of a habitat that we've got slightly less confidence in that region. So we feel it's overmapping fen marsh and swamp in this region. And to solve that, we're kind of looking at the segmentation in the uplands and updating that to create smaller segments to help represent changes in habitat in the uplands. Here we've got Northumberland coast, and on the left-hand side, you can see a nice patchwork of upland habitats there, such as bracken, scrub, bog, and fen marsh swamp. And then finally, the Broads. So this has a large proportion of arable land in it. This is classified by the vector-based classification using the RPA crop map of England. So why Live in England? It goes back to the NCA goals of providing evidence on environmental extent, connectivity and change. And we feel that the product going forward can be used to inform a number of policy and research areas, whether you're looking at natural capital asset mapping, nature recovery networks, or the 25-year environmental legislation within DEFRA. Looking forward with Live in England, it is our plan to release a fresh habitat probability map every 2 years. So the next release is planned for March 2024. In the meantime, we're working hard at refining our methodology and input data sets to try and shore up some of the classifications and have a bit more confidence in our product. An example of this is incorporating master map data to help with the classification of urban and water. And we're also looking at developing change detection workflows between iterations of Live in England products. And throughout all this time, we're also continuing to collect more field data to help improve that side of the input data sets into the product. So that has been a brief introduction to Live in England. I'd like to thank you all for listening. Happy to take any questions now or after the session. Alternatively, there's an email address there if you'd like to get in contact with the team. And finally, I'd like to say a big thank you to colleagues at Natural England, particularly field surveyors and habitat specialists, who without their work collecting the field data, we wouldn't be able to produce our product. Thank you very much.
Great. Thank you, Miles. That's lovely. So has anyone got any questions immediately now? And I should have said earlier, we are using Slido in this presentation. Luckily, it's day 3 and you're probably all used to it by now. So yeah, we take the top one then. So can you explain the reasoning behind the use of spring and autumn mosaics and not summer?
Yeah. So in earlier versions of Live in England, we used summer and winter. And we wanted to move away from winter, obviously, because it's incredibly challenging with cloud cover. We went for spring and autumn because we felt for a number of habitats we'd be able to capture phenological changes kind of in some of the uplands and things like that, that can help inform the model. However, we've not ruled out in future adding a summer mosaic back in, but there are challenges. I mentioned before that each of the zones has slightly different image dates in terms of cloud-free imagery. And some of them kind of start creeping towards summer. So if a spring creeps towards summer and then the autumn creeps towards the summer, then it doesn't leave much new imagery to create a summer mosaic from. But the kind of how we use the mosaics and how we create them is very much being investigated still in terms of kind of standardizing our workflow.
Great, thanks. And I think there's a quick second one because we do need to keep on time, but this is an easy one. Where can I access the map data?
I am really annoyed because I meant to put a link on the slides. So the easiest way is probably to Google Natural England, Live in England, and it should come up. There's the DEFRA data catalogue, I think it's called. My rest of my team are nodding, so that's correct. That is stored on, and there is also a technical report on the Natural England evidence directory.
Great. So it's been produced under an open license so everyone can get it and it's freely available. Excellent. Right. Well, I think for the sake of time, we're going to move on to the next presentation.
Okay. Thank you.
So thanks. And so I'm going to, just if you want to get ready, introduce to you now. We've got our next presentation slightly different. We're moving away from the UK and we've got João Carreiras, I hope that's good, from the University of Sheffield, and also supported and funding by the NCEO as well. And he's going to talk to us about biomass and refining the biomass estimations for developing countries to report on climate change adaptation. So here we go, over to you.
Thank you. So I'm going to present some work that we have been doing inside NCEO about using a large combination of sensors to support or to help some countries to develop some methods to report on their carbon emissions from the land sector. And this will be focused on Mozambique in Africa. So just going. Sorry, okay. So some of the background for this study. So we know that these estimates of above ground biomass are deeply embedded in some estimates of global carbon fluxes, mainly on the land use change component and also on the terrestrial land sink. Here's the latest carbon budget from the Global Carbon Project. On the left-hand side, you can see what's going up into the atmosphere. So 89% from fossil fuels and 11% from emissions from land use change. On the right-hand side, we can see that of those emissions, part is staying in the atmosphere, approximately 50%, and then 30% on the land sink and approximately then 1/4 in the oceans. However, on the land use change component, there's still a high uncertainty. So those fluxes have an uncertainty of around 50%. And it has been proven that the carbon stocks in vegetation are a major source of uncertainty on those estimates. Therefore, there are some important efforts going on to solve these issues, like new missions, like the biomass mission, and that will be important in terms of mitigating climate change. So this is just to reinforce what I said. So the magnitude, distribution, and dynamics of these forest carbon stocks in the tropics are poorly constrained, and they have a significant impact on the land use change component of this global carbon budget, sorry. And so why do we need these improved estimates of carbon fluxes from land use change? Because it will help us also constrain the geographic distribution of the land carbon sink, its trends, and to take action to safeguard those areas to maximize the carbon sequestration of these lands. Developing countries, which are the objective of this study, they are currently engaged with climate change mitigation activities such as REDD+, but most of them, or some of them, they have strong limitations when reporting carbon emissions in the land use sector. So our objective with this study was to leverage the ability of developing countries to report on their carbon emissions and removals in the land use change sector, and to improve on traditional methods by delivering multi-temporal forest above ground biomass maps using both information that the countries are collecting, such as national forest inventory data, and also bringing into that multiple satellite observations, such as LiDAR, optical data, and radar. And we used here Mozambique. And why Mozambique? Because it's a country in Southern Africa. It has approximately 1 million square kilometers. It has 41% of natural forests, and this country submitted to the UNFCCC their baseline of emissions from deforestation activities, and they are very substantial, approximately 40 megatons of CO2 equivalent per year between 2003 and 2013. And they got to these numbers by combining what's called activity data, which is the area that was deforested in the country, with ground-based estimates of the carbon stocks in the vegetation, what is called emission factors, from their national forest inventory. So what we did was to use those observations that were made in situ. So it was approximately 3,000 in situ plots that were measured in Mozambique. And we used a set of remote sensing variables. So first we brought JEDI, which is a LiDAR that's in space since 2019, collecting data. So over Mozambique, we had access to approximately 25 million footprints where we had information about canopy height. Also, we built these composites of radar data from JAXA, the Japanese space agency. So from ALOS-2, and also from, with optical data, we use Landsat 8, the reflectance product. I'm showing there on the left-hand side an example of what's the backscatter intensity from the PALSAR-2 mosaic over Mozambique in 2018, and on the right-hand side, just the NDVI over the same region. So just some brief notes about the method that we use. So first, we model the relationship between above ground biomass that was measured on the ground with a metric of height. It's called Lorey's height. And we did this for some in situ observations that were clustered. So from the approximately 3,000 observations, we got to approximately 650. Then, because from the JEDI, from the LiDAR that's in space, we can get the canopy height, we converted those estimates of canopy height from JEDI to above ground biomass, so that we get an extended set of above ground biomass estimates, approximately 50,000, that we then use to model against the radar and the optical remote sensing observations using a machine learning approach. So here are some results. Sorry. So this is the equation, the power law, that we fitted to estimate above ground biomass as a function of Lorey's height. So this equation was significant, although there's a pretty much good dispersion of values, and I will discuss this a bit later because this has implications in terms of the accuracy of our biomass map. On the right-hand side, that plot shows the validation of that model. So the model behaves relatively well up to approximately 100 tons per hectare of biomass, but then it clearly underestimates the biomass that was measured on the ground. Then, like I said, we use this model to create an extended data set of above ground biomass, and with that correlating those observations with ALOS-2 PALSAR-2 data and the Landsat 8 data through a machine learning framework, we got our model. This is the validation of the model. So it has a RMSE of 21.1 tons per hectare. So that's approximately 25% of the average observed biomass in the country. It's almost unbiased. And so most of the error comes from the dispersion, from the standard deviation. And the results from then applying that relationship to the entire country. So on the left-hand side, we can see the distribution of above ground biomass, and on the right-hand side, an estimate of the, let's say, the uncertainty or the dispersion of those estimates. So it's the standard deviation. Just some conclusions. So we were able to produce this country level map of forest biomass in Mozambique with a relative error of approximately 30% and almost unbiased. We think that we can improve this map by establishing a better relationship. If you remember, that relationship between biomass and Lorey's height, or a metric of height, was not very good. So we think we can improve this by including other variables such as tree cover or other metrics that are related to canopy cover. We also think that some of the problems that we are seeing come from using data from plots that are very small. So there's evidence that smaller plots are more biased towards estimating biomass. So that's a limitation, but there's not much we can do because we are relying on the country's national forest inventory. And we plan to then produce these either annually or quasi-annually since 2007 to then make this available to the country or to the countries to help them support the carbon reporting from the land use sector. And this is important. We are trying to engage with the national stakeholders in Mozambique and in other countries to try to enhance the uptake of these satellite-based maps of forest biomass. Okay, that's all. Thank you, and I'm happy to answer any questions you might have.
Great, thank you. Looking at those questions, they are not for this presentation. So, has anyone got a question? Oh, wait a minute. Oh, there's more sliding out. No, they're for Miles. So maybe Miles could look at those and maybe have a look for the discussion at the end of the next session. But for this, has anyone got directly relating to the biomass presentation? Okay, well, I'll ask a quick one then. Oh, is there one? Sorry. I can probably reach now.
It looks like there's a huge amount of work that's gone into that. So I was wondering about the potential for scaling this up and doing it on a much more, much broader region or even on a continental scale. Like, how many other countries are you engaging with, things like that?
Sorry, currently only Mozambique. Because this is relying on data from the national forest inventories. And as far as I'm aware, Mozambique is one of the few countries that made this data freely available to everyone. So everyone who wants to look at these ground observations of biomass can have access to the data. So that's the main limitation in terms of these analysis or this type of method. We really need access to the in situ observations. The mosaics of radar and optical observation, nowadays I think we can get it fairly quickly and easily. The JEDI data, it's all freely available. Probably it's more now I think it's available on Google Earth Engine. So I think it's pretty easy to deal with. I think the major constraint is to having access to good quality in situ observations.
Great, thank you.
Thank you.
So moving on, we next have Asima, who's going to come and talk to us. Asima Khan, she is from the University of Leicester, so here, and she's from the CLCR, the Centre of Landscape and Climate Research, and she's doing finishing off her PhD work on looking at habitat quality as an indicator for biodiversity, but particularly in areas with species poor areas, so cold spots of biodiversity. And over to you.
Thank you. So one of the main motivations behind this was to see how freely available remote sensing data can be combined with open source software to collect a lot of ecological data, which acts as a great stepping stone for conservation studies, especially in areas where there's a lack of field data or there are time constraints or lack of resources. So the main aim is to compare how the INVEST habitat quality model works in 4 sites across diverse ecoregions and different habitat types. So I focused on biodiversity cold spots because these are the areas where it's easier to underestimate the biodiversity or ecosystem functions. And also the model has not been specifically tested only for cold spots before. So the criteria here for cold spots is areas with low global species richness, high endemism containing transitional areas, or wetlands, small wetlands, or both. So I'm going to compare the habitat quality index, which is the output of INVEST habitat quality model, with remote sensing derived Ehrenberg values. So habitat quality model incorporates abiotic factors, and Ehrenberg values incorporates abiotic factors of habitat quality. So it is interesting to see how they compare, if there's a link, and if that link exists for all 4 areas. Okay. All right, so what is INVEST habitat quality model? So INVEST is a suite of open source free software that aim to map and evaluate various ecosystem services developed by Stanford University's Natural Capital Project. So their habitat quality model basically serves as a proxy for biodiversity, where the underlying principle is that area with higher habitat quality would harbor more biodiversity. So it helps to compare spatial patterns and identify areas where conservation would be most helpful. So it works by combining 3 different elements. One is the information about the different habitat types in your area of interest, and then the threats to these habitat types, which could be anthropogenic activities, invasive species, degradation. So it really depends on the type of area you're working on. And then the response of our habitat classes to these different threats, which would change from one habitat type to another. Now, when all of these are combined, you get an output, which is a habitat quality map, which with index ranging from 0 to 1, 1 indicating the highest habitat quality. Then we come to what are Ehrenberg values. So simply put, these are the numerical indicators telling us which abiotic conditions a plant prefers. So these are species specific. Now they are of various types. So it could be the availability of light, soil salinity, but here I'm focusing on moisture, soil moisture specifically, and nutrients, mostly nitrogen. So I have used proxy indices for this. For moisture, I've derived soil moisture index from Landsat 8 thermal bands. And for nutrients, I have used Tikari by Osavi index derived from Sentinel-2. And the species distribution data was taken from Global Biodiversity Information Facility. So before I compare the habitat quality index with Ehrenberg values, I need to make sure that remote sensing derived Ehrenberg values are sensitive enough to detect change in habitat conditions, specifically for same species lying within the same ecoregion. So to test this, I first did a habitat suitability mapping to find areas which had same range of temperature, precipitation, and topographical features, elevation, slope, aspect, same as my test site. And then I identified a protected area, nationally protected area within that site. So the reason I want to compare these is because protected site has restriction on which anthropogenic activities can be conducted there. So the habitat conditions would be different even for same species. So I identified 15 matching species in test and protected site, and did repeated measures for 2 of my indices, and the repeated measures ANOVA to see if there's a significant difference between the values in the test site and protected site. And the results show that yes, there is a significant difference. For moisture for all sites A, B, C, D, which are ranging from north to south, we see the p-values are more significant than compared to nutrients, but combined, they both can be used to compare against habitat quality indices. So which brings us to the results. So On the basis of habitat type, we see that natural and aquatic habitats performed way better than semi-natural and artificial habitats. So these are the two that were able to identify different ranges of moisture and nutrients in different classes of habitat quality indices. On the left, you can see the mean values of the three indices used, and artificial habitat type showing a distinct pattern as compared to the other three. Now we come to the difference based on location. So except site B, which was Pedonian grassland in Hungary, which also contains a lot of semi-natural areas and artificial areas, did not show a substantial link with habitat quality and Ehrenberg values, but all other sites did. On the left, you can see how the pattern of mean values of the three different indices change as we go from north to south. So Finland, Sweden, then Spain. And in Hungary, we see a completely different pattern of distribution within these values. So now we know that the model performs well if it is dominated by more natural vegetation or aquatic habitats. So we can use this information to link it to other ecosystem functions. For example, if we remove site B, the habitat quality index shows a very high correlation with above ground biomass. And another thing that I'm working on is to see the predictive capability of habitat quality index. So the initial results show that with every decrease of 0.1 in habitat quality index, the annual carbon stock decreased by 20 mg per hectare, and the annual water yield decreased by 15 liters per hectare. So with one index, we are able to see different values which can be used for exploratory studies when it comes to conservation. So in summary, InVest's habitat quality model can identify areas with distinct nutrient and moisture conditions, and it also shows a strong correlation with above ground biomass and water yield. Moreover, remote sensing derived proxies, when combined with species data, they can be used to detect changes in nutrient and moisture conditions. And lastly, InVest's habitat quality model underestimates biodiversity in herbaceous classes such as grasslands, heathlands, and in urban areas. So this is where we need to change the parameterization specifically for these classes. And then we have a model which is very widely applicable, especially in the cold spots. That's it. Thank you.
Great, thank you. Thank you very much for that. It's really loud now. Have we got any questions for Asma? Put the Slido up. Not at the moment. So we've got any on the floor? No? Okay, I'll ask a quick one.
Okay.
So when you chose your Ehrenberg, which ones of the factors to look at, how did you make that decision to go for sort of the moisture and the nutrient as you're out of the whole range of the Ehrenberg values?
Right. So I'm only working with open source data and freely available data sets. So my options were limited. And also when it comes to remote sensing derived Ehrenberg values, there are not a lot of proxies that can be used. So basically for soil moisture and nutrient, it was the most reliable one.
Great. Thank you.
All right. Thank you.
Okay. We'll move swiftly on then to keep to time if we can. So the next presentation, we've got the last one before a break. If we've got Wentong Xie, sorry, my pronunciation isn't great, who's come from the University of Nottingham and also the Chinese Academy of Science, and is interestingly talking the other way around. So about how a policy can there affect the environment and how we monitor the effects of policy on the ground. And it's actually links to what Paul mentioned in the very first talk about the afforestation policy in China. So that's a nice link there from this morning.
Okay, thank you and good morning, everyone. I'm Wentong. So here my talks is about the impact of afforestation policy in vegetation greeniness in China. So sorry. So here I just briefly introduce the background here, as we all know that there are different aspects which will make the impacts on the vegetation. For example, the socio-economic, the policy, and the human activities, and even the microclimate, the fire, and the vegetation structure, the species, continent, and so on, which will make the influence on the vegetation greenness and the change. And in China, the government has already give a lot of efforts and so much funding to support the ecological environmental protection, like the deforestation, like the gray to green policy, and even the machine agriculture and nature reserve. So, sorry. All right, so here I based on the whole China as the study area, and according to the different characteristics, for example, from a previous study, there are coupling relationship between the socio-economic condition, the poverty condition, with the ecological environment. Also, in order to focus on the forestry projects, and also we controlling the different sub-regions with the similar natural elements, or divided China into different separations and then did the research. So here, in order to excluding the other factors like the natural factors and human activities, how the policy make the impacts on the Chinese vegetation greenness. So here we use the fixed effect model, which have the kind of controlling variable thought. For example, in our normal research, we can control a research group, the age of the research group, like the years of the education and other unobserved characteristic. So for the more detailed and structured explanation here, we can see the figure, the dependent variable and the independent variable, the Y and X. We can see it has a relationship between them, but there was some date between them, which will have the which can be considered as the confounding factors. It will provide them another activity path, which will do the influence. So how we excluding the natural factors and then just to focus on the policy. So we use the fixed effect model here. And this is the framework. When we decided whether it is suitable for the research group, we firstly did the Holzman test and to determine whether it is have the good test result, and then we just follow to the fixed effect model. And I used the last 20 years data set from 2000 to 2020 for the MODIS LAI data as a manifestation to do the vegetation greenness, and also use the nature factors like the precipitation, the temperature, the slope, and also the policy factors, afforestation policy, in each county, how large the area of the afforestation policy in each county at the unit, and also the population as the human activities. And then we come to the results. So firstly, I did all of the whole China as the study area and do the analysis. At the results showing here, we can see that we can see a kind of obvious separation in the west and the east of the whole China, which also can follow the natural regulations, because in the large part of the whole China in the west, there are large area of desert, and in the east is a very good nature condition with the forest, with the grassland and the mountain hills. And then we divide China into poverty areas and non-poverty areas, which was a list by the Chinese government. We can see that in the non-poverty areas, the results of the afforestation policy is larger positive value, which is the better influence. And from the figure, we can see it has a large areas and the special distribution. And then when we just focus on the ecological projects, we divide into the non-implemented areas and the implemented areas, we can find some differences between them. And for the key ecological projects implemented areas, we can find a larger positive value than the non-implemented areas, which makes sense because the Chinese government make more efforts on this kind of area and give them more funding support, and also give the large other people to give too much efforts on it. And then when we did the ecological geographical division, we divided the whole China into 44 small regions, which have the similar natural elements, the similar natural conditions. We can see some differentiation between compared with the results before. It is not very obvious separation, but each region has its own analysis results. Here are listed some obvious positive results with the red circle, like in the northeast of China, we can see some green parts, and also in the middle and eastern, it shows some small subregions shows very good results. So here we come to some preliminary conclusion. So firstly, in the whole China, the afforestation policy showed some good positive impacts, but it is offset by some other factors like the population, which have the negative coefficient results. And when we compared the poverty and non-poverty areas, the non-poverty area shows the good, have the better results with the afforestation policy. And then when we compare the ecological and projects implemented areas and non-implemented areas, it shows 80% more of the better results. And when we just try to controlling the different subregion with the similar nature conditions, we can say that that each region has its own characteristic or features, and also it was some differentiation between all of the whole countries. And that's my presentation, and thank you very much for your attention.
Thank you. So have we got any questions that went on? Any in the audience?
Hi, yeah, thank you very much for that presentation. I suppose one question I have is you've seen where those differences are in how the policy is impacting on the ground. Mm-hmm. Is it now going back up to maybe looking at some changes to the actual policies themselves? So is it feeding back up to the policymakers?
Yeah, it's a very good comments like suggestions. Yeah, we try to do in the last 20 years, we try to find some documents in the government documents to figure out the specific policy, how it changed, but I didn't just figure it out here, didn't show them, but it's a very good suggestion to show in the slides. Yeah, thank you so much.
Anyone else? Oh, there is one there. Are the areas where forestation is higher now also the areas where deforestation was greater in the past? So is it being reforested where the deforestation was happening previously?
All right. So for the deforestation in the past, according to the natural observation, not only according to the LAI data we collected in the last 20 years, also according to the policy which where it focused on, we find that in the western part of China, especially the northwest of China, it have the large area of desert, and also even in the Tibetan plateau, this kind of area which is have the harsh natural environment. And so it in the last 20 years, it shows the negative, not very good performance. But after the first round, the policy from the 2000 to 2010, it shows a slow increase, but not very large improvement. But after the second round from 2010 to 2020, with the better support or even so on, it shows the very obvious and grows very quickly in the recent 10 years. So yeah, this is an explanation.
Great, and I think we've got 2 minutes, so I'm going to ask you the last final one that's on there, which is, do you have a hypothesis for why poverty-stricken areas were impacted less?
Well, yeah, this is a very good question, and I'm also thinking about this. And actually, for the poverty areas, it itself has some kind of natural features, because in China, especially in the West, as I just said, the nature condition can be a kind of cause to get into the poverty condition, because people have the less living conditions, less living environment to have the better income. So we just assume that maybe the people there have the less income, and also like the forestry projects cannot provide them with a better life, with a better income, and their living capitals is kind of a shortage. So this is the reason why it was impacted less.
Great, thank you. And as we're smack on the hour for the coffee, I'm not going to hold you up, but I do want to say that this is only the first part of this session. There's a coffee break, and then there is part 2. So come back for 5 more presentations in this area. And at the end of that, we'll be having a bit more of a discussion in general to round off the session. And finally, also make sure you check out the posters, which are linked to this topic, which are in the main poster area, which will be up today as well. So thank you, everyone, and
thank you.
Enjoy your coffee.